first lecture out of two about circular on steroids. Okay, so this is really, taking the engine replacement model and adding a lot of bells and whistles, but still staying inside the behavioral framework outlined in Rust 1987. So, of course, we're not going to look at bus engine replacements, but we're going to look at discrete choice models with more than just a binary outcome and more state variables than just mileage. Okay. So specifically, I'm going to show some results today from a paper I'm writing with Juul Hansen and Christain Carstensen from the Department of Economics here, and then with Fedor Iskakov and John Rust. So the paper is called An Equilibrium Life Cycle Model of Commuting, Residential, and Work Location Choice. So it's a finite horizon version of the model, and it's a discrete choice model where you both choose residential choice, so this could be the many regions in Denmark, and work location choice, the same types of regions in Denmark. So you have a combination of two choices that gives a number of combinations of discrete choices. So essentially just a discrete choice model. And then commuting, well, that's just the distance between the two choices in the Danish landscape. So, you got endogenous commuting. And here we're actually also going to consider equilibrium aspects. So in that sense, it's really like, putting circular on steroids more, because there we derive the demand for engine replacement, or demand for engines, and in the same way we can derive the demand for housing in this model, okay, and the supply of jobs in various regions, but we can derive the local demand in various regions of Denmark for housing, okay, based on this model. But we also have the supply within the same curve, because whenever you move, well, then you also supply your house and trade it to someone else. So it's a general equilibrium model for the Danish housing market. Okay, so we're going to add that on top today, and then we're going to continue that tomorrow. Okay, so now here's where we are in the plan. Well, we have already covered the nested fixed point algorithm. We looked many times on Hero Circle. We talked about last time how to estimate it using constraints and unconstrained optimization approaches, MPEG versus NFXP. And now today we're going to move in to talk about equilibrium and life cycle models and a large-scale empirical application based on the Danish register data. And this is what we're going to do today. So look at this paper. And then the second part on circular on steroids is going to be actually, closer to the original application. It's about the car market. So here it's about a dynamic equilibrium model for automobile markets and how consumers trade with each other. And here it's really, in the spirit of Hero Sucker, in the same sense that all the consumers at that market make choices about whether to replace the engine, replace a current car, keep it, or trade it for some other car, and then we consider the equilibrium at that market where consumers, they trade with each other and so on. So very cool, very cool. So we're going to look at that next time. And then after that, we go back to, our quest on finding out, about the properties of all these sorts of different estimation methods. And we're going to look at a very prominent branch of this literature that's based on the so-called Hotz-Miller inversion and two-step CCP estimator. So that's the plan. But for today, it's back to Hero Circle and a real empirical application. Okay, so now I want to go right to that. Okay, so one of the motivations for this work is that Denmark, as well as many other countries, are undergoing a process of strong urbanization. So you see people really, moving into the cities. The prices of houses in urban areas are increasing, and they're stagnating and falling in the rural areas. I mean, people who live in Denmark have heard the words like the rotten banana for certain rural parts of Denmark, where areas that are generally in decline. There's a reduction in economic activity, unemployment, strong sorting of unemployed and low educated people. So more and more segregation. So this is one of the things that we're going to look at and be able to look at with this model, where agents, they choose where to live and also where to work, because it's a model for that takes seriously that trade-off on whether you can live close to the economic activity. That's where the jobs are. Okay, so there's this conflict here in Denmark, when it's other areas that you have very cheap housing in the rural areas, but then you have the strong urbanization with increasing house prices and a lot of spatial concentration of jobs and economic activity in Copenhagen. Okay, so this has caused the cities to grow and thrive, but then the rural areas that just the in decline. Um, so a number of policies has been suggested to ameliorate some of these the downsides of of this development. One of them is infrastructure investment. If you can get very fast at low cost to where the economic activity is, then people should just essentially just live where they find it to be most attractive. So if people actually really want to live in the rural areas, but you just need to go where the economic activity is, well, then increasing spending money on infrastructure investments is going to level out some of those price differences and the sorting patterns in terms of in terms of where rich and poor people live and where the house prices are increasing. Reallocation of jobs from Copenhagen to the rest of Denmark. Well, that's like moving activity and making other areas in Copenhagen more attractive to live in, thereby level out just some of these economic differences in the Danish map. And so if you want to analyze policies like that, well, you need to have a model where you take into account that that people, they move around, right? Because that's what we want them to do, where prices of the houses are in equilibrium. So we have like this discrete choice model for residential and work location, where these where these choices are are key, and then an equilibrium aspect where house prices are determined in equilibrium. Okay, so the issue here is that actually these dynamic effects that arises from changing such patches is actually not very well understood, because it's an extremely complex problem. Due to several factors at play, the complexity in households' commute decision choices, job and residential mobility, and then the interaction with the housing market and and several other factors that happens over the life cycle as people get older and form families, have children, they need more space. So there's a lot of things going on here, and we want to try to capture all this or organize all these facts inside a model framework. So that's a motivation for actually building a structural model. It's also an example where we don't really have good data that can inform us of the effects of these policies. Well, now we can with the reallocation of jobs, but it's really costly to make experiments like this. And if you want to analyze and make counterfactual simulations, well, you really need to like a structural model that can inform of these policies, and it's really challenging here, right? Because there's so many things that are involved in this modeling the location and choice dynamics. I mean, dynamics are obviously crucial here, right? I mean, when you decide where to deciding to stay in the current residential region or trade your house for another one, or these are irreversible investments. There's moving cost and transactions cost, and you give up family and friends, or at least you move away from this psychological moving cost and all sorts of factors. And you have to think about being close to your job, and there's potential also coordination problems because there's more people in the household with kids in schools and spouses working in a certain area. So these are costly decisions, and when you make those decisions, it's not like you can just reverse it in the next period. So it's really an example of a choice that has strong dynamic consequences. And with dynamics come expectations, right? What's the probability I can find a new good job close to my new residence? It's not like you move out in the middle of nowhere. You make expectations about your probability of being able to get a job there, right? Or maybe you first move when you actually get a job, and you make expectations about what are the living conditions in this area. So suppose I get a potential job offer in Australia, right? I need to make this. I need to think about how is it to live in Australia. I make these expectations about what the local environment can offer. When I make a job change, I have to think about also, can I actually get a place to live, and what is the cost, and how many square meters can I get on my salary, and so on. Okay. So these things are clearly interconnected, and they're also interconnected through especially through the commute distance and the commute cost between job and residence. Life cycle aspects are evidently also important. So we're not going to work with a finite horizon model. We're going to work with a infinite horizon model, like in the Harrow-Zucker case. We're going to work with a model where households change their demand for housing over the life cycle as they move away from home, and they start finding a partner and getting children, and then children leave from home. Then, of course, the housing demand is going to change over time. Okay, and also the trade-off between residential location and the size of the house is going to change over time. So we try to put that into the model as well. And then also, it's clearly important that there's a finite horizon, right? Because you think if you're much more forward-looking in the beginning of life than you are at the end of life, because you're forward-looking in both cases, but at the end of life you anticipate that capital T is coming. So why make a big move just before you die? And so these are all challenging things, and on top of this, there's very many different regions of residence and work location in Denmark. Just think about if you did it at a municipal level with 100 regions or 98 regions in Denmark, you have 10,000 combinations of residential and work location choices. We cannot be able to go quite there, but have worked with something like 20 regions in the Copenhagen area. But we're working on trying to extend the model and deal with the computational complexity involved in this project. So, but I don't have those results for you today. So the bottom line is here, it's kind of, there's many bells and whistles, and finding an equilibrium in the housing market is actually a quite high-dimensional numerical problem. Okay, so what is it that, in a nutshell, what we're doing? We really want to build a framework for analysis where we can analyze the consequences of, for example, increased commute cost and eventually the effects of infrastructure investments that reduces them. Okay, to do so, we develop this dynamic general equilibrium model that simultaneously track a number of mechanisms. For example, choice of residence, work location, housing demand in terms of how many square meters do you demand. So it's both the discrete and continuous choice model. Commuting, which is endogenously determined once you know where your work and where your residence is, allowing for life cycle aspects such as family formation to play a key role, and retirement, and trade of houses, and sorting of heterogeneous consumers. So we have many different consumers. They're both different in terms of the age and income and whether they have children, for instance, and these different consumers, they're sorting into different areas with different attributes, and that sorting has also an effect on the prices. And for the demographic local demographic composition of people within a particular area. Okay. So this is what we can do with this model. Okay. Now, then there's this equilibrium price mechanism at the housing market. You could also build this equilibrium price mechanism at the labor market, but we just haven't built the labor demand part of the model yet, and we take labor demand as given in local labor demand in various regions as given. So this is kind of this is the model in the nutshell. Then we want to go and structurally estimate this model. And again, we move away from the bus engine replacement data and work with the Danish register data. So the Danish register data, I'm going to say a few words about that and just show you some descriptives. But in Denmark, we're in the fortunate situation where we know everything about everyone. Okay, so there's lots of heterogeneity and rich dynamics in these data. We know the residential location, the work location, the age of the individual, very detailed information about education and income and wealth and family patterns. We know who can connect people to each other through spouses and children and employers, and then we have like population data, and we can follow people over decades. Okay, so we have combined with housing prices and so on. So we have all the data actually that we need to analyze this problem. So what we do is we estimate the structural parameters based on these population panel data from Denmark, and then we show that the model fits very key aspects of the data very well. It's still preliminary work, but I think so far we're pretty satisfied and confident that we can have a very solid model for analyzing these things. I'm going to talk a little bit about in the end about what we will do to improve the model, but I'm going to show you how the model actually already now fits the data quite well. Okay, so what do we use the model for? Well, what you do is you develop a model, then you estimate the model, and then once the model is correctly estimated, use it for counterfactual predictions. Okay, so we want to simulate the effects of house prices on house prices, job mobility, residential sorting, and commuting for the Danish households into counterfactual equilibria. First, by increasing the housing supply in the center of Copenhagen. And second, increasing the cost of commuting. So you can say this is the counterfactual. What happens if we just let highways congest more and more? It's going to have for instance, an impact on house prices, and the house prices is going to increase in areas where they're already high. So, but it could also have been the other way around, or we could use a model to analyze a specific infrastructure and weight measurement. So, for instance, using Danish transportation models to figure out what is the effect on commute cost in terms of transportation time on building the Kattegat Bridge, for instance. Okay. Or building, having more capacity on some freeways, or reducing cost in general. So we're not quite there yet. So, but these are examples of what you can use models like this for. And then you simulate the effect and see what happens on house prices, job mobility, residential sorting, commuting, and all sorts of things like that. Okay. Now, before we quite go there, I think it's worth highlighting a couple of key papers in this literature that our research here is building on. Okay, it's fair to say that until recently, literature on household location decisions has mainly been based on static models. It's a huge sorting literature, and also equilibrium sorting literature, where these prices of houses and are determined in equilibrium, and you also have models with both residential and work location choices jointly. But these are mostly based on static models. Or those models that are dynamic, they are usually either residential location models or work location models, with some few exceptions. I'm going to focus here on some of those that relies on dynamic programming, since this is a course in dynamic programming, and since our paper relies on that too. So there's I think the first key paper here is a paper by Cannon and Walker in Econometric in 2011, who were the first to estimate the dynamic spatial model of location choice with both residence and work location choice. But what they did was that they actually restricted households to both live and work in the same region. So it's not a separate choice. So if there's 100 regions, that's 100 choices, not 10,000. Their focus was on a different thing. They focused on expected income changes as a main driver of migration decisions. We're going to focus on shocks to commute cost. And if you have commute cost, well, you really need those two choices to be separate, right? Or jointly determined and separate, right? Because that's the distance between residence location and work location. That's what is proportional to the commute cost. So if you want to change commute cost, well, you need to have both those choices in the model. Then there is that's an other recent econometric paper by Pat Bayer and co-authors Tim and Macmillan, and I'm blanking on the last one. Sorry about that. And they developed a dynamic equilibrium. Dynamic model of residential choice and a residential choice, so not a work location choice model. And they use some of the methods we're going to talk about a couple of lectures from now that are based on these computational, more light methods of sequential estimation, where in the first step you estimate reduced form policy functions from the data, and then you by inverting some of the Bellman equations, you can simply reduce the problem to a static model and avoid actually solving the dynamic program during the course of estimation. Of course, you need to solve it when you want to make counterfactual predictions. Well, their focus there is on something different that we do. They look at marginal willingness to pay for various non-market amenities, like for instance, crime and air quality, these kind of things. They work with an infinite horizon model, so they fully ignore the life cycle aspects of the residential choice. And as you'll see, there's clear life cycle patterns in the data that we felt it was very important to account for. And then they do not actually solve the model to do these counterfactual simulations. The closest paper that we are building on is a paper by Moshe Bushinsky and co-authors. It came out in Econometrica 2014, which is the first model to actually first dynamic model to jointly model the residential and job location choices in this dynamic structural framework. They also have another, on top of this choice, an occupational choice for being unemployed, blue collar, and white collar. So a quite rich model. They estimate this model on data from Israel on Russian immigrants or immigrants from the former Soviet Union to Israel. So a very selected sample of a particular group. And what they analyzed was how their residential work location choices were and how it affected their occupational choices. They were taking the prices, the house prices as given, which makes a lot of sense in a situation where you only model the choices of a small group of the economy. But once you move on and want, like we do, use the entire population to population data to estimate the model and run counterfactuals that not only affects Russian immigrants in Israel, but affects the entire population and has price effects and want to analyze the effects on prices, well, then you need an equilibrium model. And that's why we are working with equilibrium counterfactual simulations. There's another nice paper by Florian Oswald that came out in QE recently. This is the life cycle model of consumption, housing choice, and migration in the presence of aggregate and regional income and price shocks. And it's another very nice paper, but they do not distinguish between home and work location. So very much in the spirit of the paper by Walker, but then with a continuous choice of housing and consumption and housing investments. So that's analyzing this problem from another angle, more focused on how migration elasticity varies between owners and renters and stuff like that, and it is a housing investment in this model. So a little bit different. Here's another example. This is actually a static general equilibrium model, because what is common for all these dynamic papers, the Ken and Walken paper, the Bayer and co-authors paper, and Bushinsky and Oswald, is that while they're dynamic, they're not explicitly focused on equilibrium, and there you would have to go to the equilibrium sorting literature that is then mostly based on static models. So what we're doing is really that we're combining these two literatures to be able to say something about the equilibrium price dynamics at the housing market and residential and work location choice dynamics and commuting patterns, how that changes over the time as you make shocks to the economy, like building or investing in infrastructure or subsidizing housing in urban areas, or whatever you want to do, counterfactual we want to do within this framework. Okay, so I'm going to now talk about the data that we use to estimate the model. Okay, so like I said in the beginning, we have very rich data in Denmark. Okay, so here's a short outline of the data sources that we're using here. So we use the Danish administrative data from the period 1992 to 2015. We have access to the population, so everybody is in the sample. There's no attrition other than death and moving outside the country. Okay, so this is like Big Brother watching you. Okay, so we're combining like a bunch of different a bunch of different registers. One is residential info that gives information about what the regional, municipal, parish, the zip code where you live, and moving in terms of the actual date. We can annualize all of this to have a model, an annual model. The discrete choice is made every year, but in principle, we actually observe the date. We have lots of information at the individual level that can also be combined with information about who you're married to, who your children are, who your parents are, and so on. So, age, gender, spouse ID, kids ID, all these sorts of data. And then we have from the residential register, we have house characteristics, which is actually what house do you live in. So you can not only link persons to persons, but also persons to the actual houses, which means we can actually observe who's trading with whom at a given time. So we can follow houses from owner to owner, if you will. So we have data on house characteristics, such as the house ID, the number of square meters, number of rooms, even number of bathrooms, stuff like that, the year of construction. We're going to use only a fraction of all this data because we need to, we're going to be hit by the curse of dimensionality before we run out of data. But still, this gives a lot of possibilities to a lot of modeling freedom in terms of choosing the right variables to enter into your model. We have data on the on the labor market, employer ID, job industry, occupation, employment period. Employment location. We have data on income and so on, educational attainment. So very, very rich data. Okay. So I can continue talking about how rich this data is, and all the details. My point with this is that Denmark is actually one of the coolest place to be if you are interested in doing structural estimation of dynamic programming models, because we can follow at the very detailed level key economic indicators and background variables for the entire population. We can link people with each other, and then we can follow this entire population over a long life cycle. It's also great to be in Denmark when you're interested in studying general equilibrium, because we have the entire population. So when you actually go out and estimate conditional choice probabilities of moving, well, it is actually a good population estimate of what the actual choice probabilities or market demand for living in a particular or moving to a particular region actually was in that year. So you will also see at the end that since we're working with this population and the prices are determined in equilibrium by this population, it's actually, the model is predicting that the prices that come out of this model is actually very much in line with the observed prices that we see, which is, one of the very nice thing about having access to population data. You don't have these issues of endogenous selection or small sample problems. So this is just, great data. Okay, so we have lots of data we can add, and I'm not going to talk about this. Well, since this is primarily a Danish audience, my dynamic economics class, I think you see in the picture of Denmark, this is essentially where people live. This is Copenhagen, you got Fyn, and you got Aarhus. These are like the major cities, and Aalborg up here. This the red areas mark just where people live. So this is population density in 2016. We're going to focus on our analysis on this particular region, and we're going to cheat a little bit, just say we cut out the rest of Denmark for now. This is work in progress, and then we have the Copenhagen area and then the rest of Sweden. Okay. So this is the area of analysis that we're working on. And we're working on residential choices where your choice would be one of those different regions here. So like Copenhagen municipality, that would be, if I choose to live there and work there, that would be one of the choices. If I choose to live in Albertslund, which is right down here, then or somewhere here, then that would be a work location choice, and then you can live somewhere else. Okay. Okay, so there's been changes in population density. I'm not going to talk much about that. Everybody knows that people are moving to the cities, and this is what you see. You also see that in the prices. And so here's the sales price per square meter in various provinces in Denmark over time. So these are slightly bigger areas than the ones I showed on the map. You have on the top, you have Copenhagen, which is the capital of Denmark. And the bottom, you have like the small island Bornholm. Maybe I can find it on the map. I think we even excluded from the map, so it's so far away. Okay, sorry about that to Bornholm. But we have southern parts of Zealand is going to be the red ones here. These are examples of cities in the bottom of the price distribution, and this is going to be located down here where the population is also more thin, and you'll see that the house prices are also lower. So generally, this is not super surprising. The prices are higher in the urban areas, but the key thing that has been happening over the last decades, essentially, is that those prices has been moving away from each other, and the price differences between urban and rural areas has just been increasing. Okay, so the model we have here can actually explain that fact from just the fact that there's increased economic activity in terms of jobs and investments in various amenities in the Copenhagen area, and also from increases in cost of commuting, both in terms of time and money. Okay, here's another outlook from the data. So when you start to build a model, you would like to see if there's some regularities you can use as a simplification. Okay, so here's one example of a regularity. You got square meters here on the x-axis, and you got the house price on the y-axis. So I mean, it's not surprising that the bigger the house, the more expensive it is. But it is pretty striking if you look at this that it's so quite linear. So there's some intercept, and then there's essentially just a straight line. So as you increase the price as the size of the house, the price is going to increase just linearly. This is true only if you zoom in on the specific regions where the houses are homogeneous enough in terms of the square meter price, because otherwise you would have a mix of big houses in urban areas, for instance, and smaller houses big houses in rural areas, and smaller houses and apartments in the urban areas where the square meter price is high, and then it would not look like a straight line. If you combine those, it would probably look like a mess, or in the best case, a curve. So once you zoom in on a specific regions, these are different regions of residence in Denmark. I can't remember this is going to be Copenhagen, but if you but if you zoom in on each of these, no, this is not right. Number 5, that is Gentofte, the most expensive area here in our sample, which is a little bit north from Copenhagen. But here you see the square meter prices are roughly constant within across sizes of houses. So what can we use this for? Well, we're going to use it for modeling, making sure that we determine the prices of houses. They're simply just a simple function of the size of the house. So you will see that later when we will look into details on the model. So another thing, once you start looking at the data, you look at, say, what's the probability of moving residents somewhere. Plot that over the life cycle for singles and people in partnerships. Well, you obviously see this is dependent on age. And like I said in the beginning, you don't want to move when you're close to dying, right? Incur a big moving cost and all the hassle. You just don't do that. But there's also other underlying features in terms of why there's so much mobility in the beginning. Of course, in the beginning maybe you didn't actually find the right house to begin with, and then also you have less restrictions in terms of lower moving costs because you have less coordination problems when you're not in a partnership, or if you haven't got children left, maybe you didn't have you settled your final job. So that's why people are so much mobile in the beginning. If you divide it into partnership singles, here you see singles that are just more mobile, whereas people who are married there or cohabiting, they are less mobile. It makes a lot of sense. If you divide it into people with children or not children, then you see people who do not have children, they have higher moving propensity, and they're less or they're more likely to move compared to people who have more children. The more children you have, the older they are, the less or when they're in schooling age, they're less likely to move. So here's actually a moving probability across, measured in terms of the distance to when the child is born, and you see the moving probabilities of households are somewhat higher before, and then actually there's a peak the year where you get a child. You need to figure out where to find space for that, or find a more permanent residence for your new life. And actually, I should probably have continued further out here, but what happens around the schooling age is that then the probability of moving actually falls even more. So these patterns in the data, well, these are of course important to capture, especially if you care about how if children, how various types of households, like families with children and without children, how they are going to move if you make a counterfactual policy change. So, for instance, if you suddenly move people's jobs to another place, well, who's going to be willing to make that move? And obviously, people who are in partnerships and have bigger families, they are less mobile. So, but here's an example. There's so many things going on at the same time that's just not possible for the human brain to disentangle all these things. So therefore we need a model to organize our thoughts and all these different mechanisms. Okay, so here's more moving probabilities. This is by labor market status. So generally, if you have a full employment, then you're less likely to move. If you're are unemployed part of the year, well, then you're more likely to move. And sometimes it is also triggering a move, simply just because you need to search for a job in another region and you don't want to move to or commute too far, or maybe you lose your job and you need to move out of your house and find some other place that are cheaper to live. Okay. So we talked a little bit about in the beginning about the residential and work location choice model that simultaneously. And here is actually a graph that shows that this simultaneity is actually quite important. So the first column here shows that the fraction of people who do not change their job when they move their home. Okay, so they're not changing jobs. So this is basically people who are within a period before or the period after or the same period is not moving their job. Okay. So this is 55% of the sample. So, some people are just moving around and only moving one thing. But the rest of the population, which is close to half of it, is making a move either the period before or the period after. Okay. And here you have the people who make the move the period before or the period after. Here you have the people who are making it both before and after, and maybe even during. So you see that job or residential move trigger job moves, and so the simultaneity in these two choices are evidently important. You can also see that the most frequent thing to do is actually this is this bar over here. So you change the job in the same period as you change your residence, especially when you look at people who make far moves. This is the case. Okay. Otherwise, you have people right here. These are people who just changed their job and then they moved afterwards. So people tend to move their job first, and then you have it vice versa. Okay, so you first move your residence without a job, and then so on. So this raises the question: if you were to model this in a static framework or a model with a finite, very few number of periods, right? Without dynamic programming, you would have to make a stand about whether you were moving one thing first or the other, or just combine the whole thing in the data. But here, since it's a sequential choice model, where you every period make a choice making expectations about your probability of finding a new job or the prices in certain areas. It's not like if I first make the move, I can make the job move. I can make a residential choice next period, right? And in fact, you're going to be more inclined to do so if you've already moved, because now there is a bigger distance to your job, and so you can both have in these models, because of these sequential choices, where you make every period a choice whether to move residence or work location. You can have both moves forth before and after. Okay, and the model actually predict this, is able to replicate these dynamics. So this is another example of where you would really need like a dynamic model to analyze moving patterns. Okay, so just to sum up here, the key factors that we want the model to capture is the increased urbanization that leads to increased regional price dispersion between urban and rural areas. That's why we need an equilibrium model that allows for an increased concentration in urban areas would have a price effect on the houses. Okay, you need simultaneity in the residential and work location choices. Otherwise, we couldn't capture the dynamics that is displayed in this graph here, right? I mean, this is definitely a simultaneous choice, and it's also a sequential choice because people, they just move both before and after and during the same period. And then a few things about what's happening with residential mobility. It's falling with age, moving distance when you're full-time employed, when children arrive, when there is more than one person in the household. So because of Juul coordination problems. Actually, Maria Juul Hansen, she's working on exactly modeling that. We're just going to make a reduced form approach to this and allow moving costs to differ across households with more than one person. But she actually tried to model the whole 9 yards by doing the family economic style collective dynamic collective model, where both partners are choosing the residence and the work location. So job mobility falls with age, increase with education, housing demand. Well, that's increasing with family size and income. It falls with prices. There's a trade-off between location and size of household. Not all of this is shown, but you can look at the data and slice it in so many ways. These facts, these stylized facts, they're just very, very clear. And then you saw that house price is almost perfectly linearly in size. So, with this, building on these facts, these stylized facts, we want to have a model that can accommodate these features of the data, estimated on the Danish register data, observations on the individual level choices, on where you live and work, panel data on that, and then based on various factors like age and marital status, and also model the income process for the households. So that's what we're going to try to capture. And so now let's see if we can do that in our choice model. And I'm going to start with the choices and the state transitions. There's two discrete choices marked by D, and you choose a residential location, which is signified by the superscript RL for residential location, and then you choose a work location signified by WL for work location. Now in those two for those two choices, you will have to choose one of our zones. Okay, so when you choose a residential location, it could be like one out of 98 municipalities in Denmark, in which case R would be 98. Now for the empirical application, we're going to focus on 20 zones or 20 municipalities in the Copenhagen area, and including an outside option, which is going to be the rest of Zealand. Okay. When you choose your work location, you actually do not choose your work location, because you can not be sure to actually get a job in any work location. I mean, if there's no jobs, you can choose to search for a job there, but you will not get one. Okay. We're going to describe that state transition for the work location state in just a second. But what you can choose between is the intended work location, which is going to be one of those R zones. You can also choose not to search for a job, or you can choose to simply just voluntarily be unemployed. Okay, in which case the decision would be the empty set. Okay, or we mark this sign here for the choice of unemployment. Okay. Then there is a continuous choice for how many square meters to demand in the residential region that you live. Okay. And we're going to treat that actually as a static choice, and I'm going to show you just in a second how that simplifies the model. Okay, and we do that to avoid having an additional continuous state variable, which would be the number of square meters of your house, and a fully dynamic choice where you would have to solve a continuous maximization problem, the Bellman equation. So we would like to avoid that. Okay. So this is not, an assumption that we really like, but it's buying it a lot in terms of tractability. Now that's a decision variables. So let's move on to the state transitions. So there's age. Okay, now age is just deterministic. It moves upwards, and you can't do anything about it. So that's a deterministic transition. We start by following people from they're young until they're like 100 years old. Okay, and then you can die with some probability on the run. Okay. Then there's the two key state variables here in the model. Okay, so these are discrete state variables. The residential location, or RL, and the work location, WL. This is where you wake up in the morning and make your decisions. Okay, you wake up in the morning, you say, okay, I'm in Copenhagen, I work in Albertslund, and then I make my decision. Okay. But before that, I kind of check if I'm married, and I check if I have children. So these are two additional state variables, and I know my educational status, which is not changing. Okay, so the marital status and the children's status, we can lump those two variables into another variable we call X, we'll see later. These are the non-location endogenous state variables, or time-varying state variables. So marital status, that's binary. So we consider people being single, either single or married or cohabiting. Okay, so Denmark, that distinction is not a big deal. That's the process for that state variable is governed by a first-order macro process for the marital status, but then conditional on your age. Okay, so you can say here that partners is essentially arriving and leaving you as manna from heaven. Okay, so it's like you can't do anything about it. It's just a stochastic process, and it's not determined by anything you do with respect to the choice of residence and work location and the house size decision. Okay, and any of those counterfactuals that we can do, we can assume that's not changing that process. Okay, so yeah, okay, so it's and the same thing with children, and you say maybe that's even more scary, that you can stochastically, without maximizing any utility function or making choices, you can get children. But it's a way. The alternative would be to a full modeling of contraceptive choices and finding partners and fertility, and how does that play into with the labor supply decisions that are encountered in the model and so on. And I'm not saying that it's irrelevant, but it's we think of these processes as a second order an approximation that where the error is kind of second order relative to what we are looking at, right? We're looking at the effect of infrastructure investments and increased housing supply and moving jobs and stuff like that, and we want to look at the effect of house prices. So we're going to make an approximation here. Okay. A final thing is the educational status, another state variable that take three values. So we don't have accumulation of human capital. We don't have schooling choices, stuff like that. We just treat education as a fixed type. And we really want to have education in the model, right? Because we want to see how highly educated people who with higher income prospects and has higher income expectations, how they move around in terms of residential location choices and work location choices, where they're working, and how does that affect that sorting affect the house prices. So it needs to be there. Okay. you can have a less a medium cycle. Medium cycle is corresponding to a BA, and then you can have a long cycle where we lump masters and PhD together. Okay. Of course, these are examples. So this is essentially like 3 years after high school. Okay. So there's many other applications where educations will not get a bachelor degree, but this is like roughly like corresponding to 3 years of education. So lots of skilled workers are in that category, even though they didn't went to university. Okay, so here's the choice model. Okay, so the agent is, well, as usual, maximizing the sum of discounted expected utilities, and doing so by choosing these three discrete, or the two discrete choices of location, and then the continuous choice of housing demand. Okay, and how's that per period utility comprised of? Well, that's a per period utility U, and we're gonna look at that just in a second. Essentially it's this usual state and decision specific utility function, and here in here we define this X, which is now marital status and children status, and then you have the location state variables, and then you have the decision, which is the discrete decision, which is a vector that combines both residential location and work location, and then they have the continuous choice in square meters. So you want big houses, but you will have to pay for them. All this stuff is buried inside here. You want to live close to your work. You want to live in areas with nice amenities and so on. So we try to model that inside the utility function. Okay, and then the individuals, they discount the future, and you don't have to have like beta always. You can allow for survival probabilities being state dependent, and thereby having people discount future more. So we're actually not doing that in the present version of the model. We just have the survival probability discount factor being equal to beta, which is fixed, equal to 0.95, which is something we have to do something about, but we haven't done yet. I mean, what you do is you essentially go out and you say assume some subjective discount factor, and then hold either you estimate it or you set this discount factor, and then you can go out and potentially estimate survival probabilities from life tables and see how they vary with marital status and education and age and other state variables are in the model. So you can actually account for that in the life cycle model, and we will put it right in here. Okay, so I think I've pretty much been through the most things here. Well, you also have the fixed types, which is going to be educational status. So even though I think I said that educational status will follow a markup process that depends on age, we actually just going to treat people as fixed types in the results you're going to see. Okay, so here's a utility specification. So the utility specification is essentially a quasi-linear utility function where you have the first part here, which is the utility of consumption, the utility of consumption, which comprise of a marginal utility of money and then the amount of consumption that you have beside the housing expenditures and cost of commuting. Sorry, cost on moving. Okay, so that's one part of the utility. Then there is utility from housing services, and you see this is a quadratic function, and the amount of square meters that you have, and the idea here is you like to have a bigger house, okay, to some decrease with some decreasing marginal utility. Okay, so we allow for that. Then there's going to be commute cost. Commute cost, well, they depend on the residential choice, right? Because if you choose the residential and work location choice, so the entire vector of discrete choice. So if you choose to live in far away from where you work, well, you have to commute more. So and those commute costs, we could potentially allow those to depend on the non-location state variables if we wanted. I mean, anything you could actually let depend on what is coming in. So the non-location state variables, the location state variables, and then the decisions or the next period location state variables and the housing decision. Okay, so I'm going to show the functional forms when we go through the empirical results, because then you can see the parameters right next to the estimates. Okay, so in some of the places, or we have the marginal utility money here is really not just a parameter. You can see it depends on S, which is the entire state variable vector. So this is everything that's coming in here, both X and D, right? And so you can allow for and also the type. So you can allow for basically the richer people putting lower weight to money, maybe because they just not only have income, they also have wealth, right? So you can allow for that, and this is a way of trying to avoid modeling the entire intertemporal allocation of assets and wealth accumulation and income shocks and so on, and consumption and savings and investments. We just essentially have a reduced form for what the marginal utility of money is, and we put it right in there. Let it depend on income. Okay? And then you have consumption, which is going to be income minus the cost of the cost of living in a certain region demanding H square meters. Okay, so what do we have? This is the price per square meter in residential region, or L, that you choose to live in, and then you have your demand for square meters. So we multiply these together we can do that because of the linearity of the house prices in the size of the house. Okay, that could be a constant there, but that's going to be washed out in the that's going to be washed out or put into regional fixed effects, which would be inside these amenities. Okay, so we're not going to worry about that. And then, so this is essentially like what is the price of purchasing a house in a certain area? We're going to treat everybody as virtually renders. Okay, so and this parameter, which we're going to estimate, is sort of say what is the percentage that you would have to pay for a house of a given price in that region. So we call that the parameter that indexes the user cost of housing. Okay, so we estimate it to something like 7% of the house value, which is not totally out of the realm. So what do we have here? This is like a moving cost, monetary moving cost, and this could include both moving cost and residence. Okay. Moving cost of residence, or it could be moving cost of moving job. Okay, so we can parameterize all this stuff. I already talked about utility, housing, commute cost, and amenities. We can allow for here regional amenities this could be regional specific fixed effects, but it could also be variables that describe how cool is it to live in a certain area measured by some observable. So if you want to if you have variables that are essentially regional specific and proxy that, you can put it right in there. So like what is the number of restaurants, school quality, how close it is to the water, regional amenities that describe how much utility a given region get out of living in that particular region. We can put into amenities. Okay. And I think I think you have utility cost of moving, or psychological moving cost, both in terms of residence and work. Now we can, for the work location move, we already have a lot of frictions, and I'm going to show them, because you can't make sure that you can't you're not guaranteed a job even if you're searching an area. So that's implicit a cost of moving, right? But we're going to model that explicitly through the job search process. Okay, so you can say this, we're going to model, within the period, actually model the choices sequentially. So we're first, you choose the work location, then you choose the residential location, and then you choose the continuous choice of square meters. Okay, so I'm going to start with the last one. And one of the things I already alluded to was we're going to ignore the dynamic implications of the housing demand, which essentially makes the choice completely static. So what is an example that we're ruling out? Essentially, that there could be adjustment cost in changing your house size. Okay, and of course, this is really an approximation, but the alternative would be if you wanted to allow for adjustment costs, so you can't just change your house every single period without any cost, well, then you would need another state variable that says something about, okay, what's the size of your house, and and then you need to know what's the price last period and the next period and so on, right? So we just assume people are renters, and then they can so we want to avoid that additional continuous state variable, the house size, and we want to avoid having a complete continuous choice where we need to numerically maximize the choice specific or housing demand specific value functions for each state and for each discrete decision throughout your entire life. So that could potentially be done, but then you would have to sacrifice something else, and we think it's important to have more discretization and more state variables, and that's a priority we have. So, but why don't you just leave it out? Well, the reason is it's super essential we have the trade-off between both the location in terms of the residential location choice, and then also the house side, because there is a trade-off here. You can't have both. People will have to earn money and spend them on housing expenditures, but if you want a big house in the center of Copenhagen, you're going to spend a lot of money. So there's a trade-off here between location and size. Okay. Now what we're going to do here is we're going to assume the static choice, which essentially means that the next period value function is totally independent of the housing demand, and this gives us that optimal housing demand H can be simply just found by solving for the first order conditions, which is if you look at this, differentiate this guy, you see H is appearing here, and here everything, because of the additivity, is just canceling out, and all these other terms are just independent of H, right? So this is irrelevant, and all this stuff here is irrelevant, and then you end with these first order conditions here. Okay, so this is like the derivative of the utility of housing services, and then you got the negative marginal utility of money minus the price. So you solve for that, and you get essentially the housing demand. Okay, so this is like the optimal housing demand, and now you see here this coefficient here on the linear term in the utility function that determines the level of the housing demand. And again, we made marginal utility of money a function of the state variables, we can have that being a function of the state variables. So we can have families with who are married and have children, and they will demand larger houses, and this could also this would also depend on say your educational level and so on. So you can have state variables pushing up your preference for housing throughout the life cycle. Okay, and then you subtract the marginal expenditure, essentially, right? So in other words, this parameter here is going to be negative, right? Because if we have decreasing marginal utility of housing, so when prices increase, well, the demand is falling. So this is how it should be. So see, what we're going to do now is we're going to substitute the expression for the optimal housing demand H star into the utility function, and we end up with what we call like the indirect utility function given or conditional on the other states and conditional on the other choices and the states. Okay. Now you're going to see several places I have now removed time subscripts, and I've not managed to remove this one here. This is just to, on some equations, it just makes notation a lot really cluttered if you have to carry around plus t plus 1 everywhere. We are still in the framework of a life cycle model, okay? So it's just to make things appear simple on the slides. It's written correctly in the paper. Okay, so having substituted that into the utility function, so you work with the indirect utility function in the optimization problem, you essentially boil the whole problem down here to a discrete choice problem, because now we've put in the optimal housing here, and then only those two discrete choices left. Okay, so that's what we're going to try to solve now. Okay, now for the discrete choices, are like number 1 and number 2 in the sequence. Okay, so we're gonna have a sequential choice with first you choose work location, then you choose residential location, and then you choose age. Okay, and like we normally do, we always, when we have sequence of choices, you start with the last one first, and this is the one we just covered. Okay, so when you then move back and choose the residential location, well, then you make expectations about what is the optimal amount of square meters I'm going to demand in that region, RL, that I'm considering choosing, and what is the corresponding expenditures, and in the end, what is the indirect utility of choosing that region, taking into account that in each of the regions, I'm going to optimally choose the housing demand according to the solution I showed on the previous slide. And then you move back and choose work location. Okay, so the sequence of choices is, you wake up in the morning, you look at your state variables, you figure out how old you are, where you live, and where you work and where you live, and in here you got your partnership status and the number of kids, and then you figure out what to do. Okay, so this is what you do in the morning, right? You look at your state variables, and then after that you go out and say, am I happy with my current job, or should I go out and find another one? So then you make an intended work location choice, and then there's going to be a job search process that leads to a realized work location choice. So we're going to discriminate between the choice of search, or the intended work location, and the realized work location, which is going to be the end of period work location, okay, or after job market is closed, if you will. Okay, now conditional on that, well, then you go further in your sequence, still happening within the period, and then you choose your residential location conditional on where you have ended up. Of course, when you make that choice, well, then you think you think about, when you choose a residential location, you think about what is the probability that I get a good job in a good region, and you think further than that, and think about if I end up in region WRL, what is the utility associated with living there? And you make expectations about that. So we're going to formalize that process in just a second. Now, after that sequence of choices, you enjoy consumption, including the housing consumption, or the utility of housing services, for the rest of the period. And then you just, you go to bed, and then you wake up in the morning, and then you're 1 year older, and you have a new set of state variables. So that's how it works. Okay, so let's look at the possible transitions in the job search process. So that's essentially that era here. So how do you get from intended work location choice to the realized work location choice? Now, see, this is actually this choice, this discrete choice, is a little bit different from the choice in the Zucker model, because in the Zucker model you would actually observe what Harris-Zucker does. We don't observe where people think about going. We observe the realized work locations. This is going to be what we observe in the data, and we're going to actually integrate out that job transition process with multiplying with the relevant job transition probabilities and so on, when we derive the likelihood. But we'll come to that. Okay, so here's the possible job transitions in the job search process. So first, the work location transition probabilities for when you are searching in a particular region looks like this. Okay, so we're going to consider 3 different transitions. So if you choose a work location WL, this is what can happen. Okay, 3 things can happen. Okay, the next period work location can either be where you searched, it can be where you are now, or you can end up in unemployment. Now, this is going to be if job search is successful. So this is what I've written here, and that happens with probability pi n. Okay, so pi n is so to say the probability of arrival of a new job. Okay, and that is depending on where you search, it's depending on where you are now, and it's also depending on whether your other state variables, if you're married, or in fact also on your type, which we're gonna which we have suppressed here. Okay, so your educational status, okay, and children's status and so on. You can potentially allow for that. Okay, but most importantly, it depends on where you search, right? So if you search for a job in the middle of nowhere, nobody is gonna, give you a job. There's no jobs, and then this is gonna be low probability. Okay, so this is the way we're gonna put functional forms on that later. But just think about this: different choice arrival probabilities throughout the Danish landscape. Okay, so the consumers will take that into account when they make the choice. Okay. Then you can end up in the same region as you were before. Remember, you wake up in the morning in this region, right? So this is your state variable, and that happens with the probability one minus probability of getting a new job, because if you don't find a job, you get that, and then you have to multiply with the probability that you actually keep your current job in region WL. Okay, again, that can be state dependent. It can vary across regions. So in some regions, there's just more turnover, or for maybe for older people, there's a lower probability of keeping your job, or lower educated people, there are more turnover and more firings. This is an empirical matter, and we can go out and estimate those probabilities, and that's what we do. Okay, as a integral part of the choice model. Okay, and then you can also end up in unemployment, even though you have not actively chosen it. So this is involuntary unemployment that happens if job search is unsuccessful. So that is 1 minus pi n, and you're not able to keep your current job. So 1 minus pi k for keep. Okay. So these are the three different job search transition, or job transitions that can happen if you search for a job in a particular region DW. Okay. Or the region you search in is W. Okay. So let's move on here. So you don't have to search for a job. You can also decide not to search for a job, in which case there's two outcomes. Either you keep the one you have, so L t plus 1 is equal to WLT. So that happens with probability pi k, okay? Unless, of course, then pi k can be equal to 1 if your current work location state is unemployment. You can stay unemployed with probability 1. But this could also be an outcome if you have a job already, and then you would lose it with probability pi k. You would only keep it with probability 1 pi k, but lose it with probability 1 minus pi k for probability of keeping. So for currently unemployed individuals, well, then if you want a job, you would have to make a decision of searching in a particular region, or choosing an intended job location, and that new job you will only get if you actually successful in the job search. Okay, so if there is a good likelihood for searching for a job for getting a job in a given region, that's going to be high. Okay, or you can stay in the same state if you're not successful with your job search. You can also have voluntary unemployment in this model. Essentially, if the individual chooses to just stop working, that is DW equal to the empty set, or to unemployment, well, then with probability 1, you're going to be unemployed next period. So there's perfect control here. You can essentially just decide to stop working. Okay, and in that case, t plus 1 is just going to be unemployment. Okay, so these are the possible transitions in the job search process. Now, moving on. There's one thing that's worth realizing here. When we're solving the model in the Bellman equation, we're solving for the expected value function. So this is the next couple of slides is going to be leading us to the expected value function that we call EV. Okay, and the crucial thing here is that the expected value function only depends on the region that you end up in. Okay, so there's no memory in how you actually get there. So you don't need the combination of both the current state and the location state and the choice of location. Okay, which reduces the dimensionality hugely on that state variable, which is on that object, the expected value function. So that's something that you need to realize and utilize. It's a property of the model, so it's not an additional assumption. Okay. So, but let's move on to the residential choice. So now we're in the second last choice in the sequence of choices here. So we're moving here. We solved this, and now we described this job search process. Okay, so we're going to move back to the sequence of choices, and now we start with the residential choice, and we move up to the work location choice afterwards. Okay, having described all this. Okay, so first the residential choice. So this is like number 2. Okay, and here to recursively to do the, we need that to. So we're trying to now do the recursive formulation and consider the Bellman equations. Okay, so first I'm going to just define something we call EVR. Okay, so superscript R for residence. Okay, let that be the x and the expected value of residence R. Okay. Again, I moved L just to make notation a little bit more compact. So whenever it says R, just think about RL, okay? And whenever it says W, just think about WL, okay? In these superscripts. Anyway, so this is expected x and the expected value function. What do I mean by that? So this is before it's before you're learning about your epsilon shocks, okay? We haven't talked much about those epsilon shocks, but they're going to be 2 epsilon shocks. There's going to be one that is realized when you make your decision on the residential choice, and there's going to be one that's realized when you make the decision on the work location choice. And the first one that's going to be realized is for the work location choice, and then the residential choice. Okay, so at the point where you're making the residential choice, you already know where you end up living, or when you work your residential choice, you know where you end up working. Okay, so we are in the second process after this already happened. Okay, so the expected value here is basically conditional on the employment location outcome from the previous work location choice. Okay, so job search has already happened. But it's before learning about the residential location choice. Okay, so then that expected value, well, you make expectations over that epsilon here, and it looks like the usual log sum, because guess what? We're going to assume that is I at extreme value. Okay, now there's going to be another shock that we call epsilon W. That's also at extreme value. They have different scale factors, and then because of the sequence, we're going to end up with choice probabilities and expected value functions that are akin to the nested logit model. So it's like a nested choice, right? First, the first branch is a work location, and then there's different branches beneath that in terms of the residential location. So we can look at the bottom of the branch now. Okay, so you got the log sum over the utilities of living in the realized work location and in the chosen residential location here, and then you take the expected max with respect to those. That's essentially the log sum over all the alternatives. Okay. Now this guy here is the expected value function. This is what we're solving for, and because we have a finite horizon model, it's going to be an expected value function at each time period. Okay. Note here, it only depends on the work location and residential location that you end up in. Okay, so not a combination of both work location and residential location state, and then the work location and residential location choice. Okay, well, but you need it inside the utilities, right? Because there's moving cost and frictions there. So you need that in there, the moving cost. But that's outside in here. We can always calculate that in closed form. That's once we have the model specified. Okay, and then this the sigma r, that's a scale factor on that I at extreme value term. Okay, so given you get the I at extreme value state variables, then you can also bag out what the probability distribution is for the discrete choice of residence or the conditional choice probabilities. Okay, and these are multinomial logit with the same input as you have here. Okay. So that's the residential choice. So now we move backwards again in our backward induction inside the period and make the work location choice. So this is the first thing that the consumers do, but it's the last thing that the programmer is doing. Okay, we're doing backward induction. So here, correspondingly, let EVW be the x and the expected value associated with the location WL or RL before learning about the work location taste shifters or work location shocks. Okay. So this is the deterministic part of utility, but it's also before learning about the outcome of the job search process. Okay, so you're going to have here the expectation with respect the expected maximum value with respect, or taking the expectation with respect to the ID extreme value shocks is going to be the usual log sum formula here, but in here we're going to have the expected choice specific value corresponding to a particular choice. Okay, so this is like now we are integrating over that guy here. Okay, now that's what's going on inside the log sum. Okay. One of those guys here. Well, remember, it's not like Harris Sucker now, right? You don't choose your work location. You choose where to search, and then you can end up in that work location. So we need to integrate out the choice, the transition probabilities pi here from the job search process. Okay, so this pi here, well, that's a combination of all the different pi's that you have in the previous slides, pi k and 1 minus pi k, depending on what transition you're looking at, that we had on all these slides here. Okay, so this probability density is kind of the convolution of those two slides here. Okay, so all those here are just are in the transition matrix here in the different points, depending on the type of transition you're looking at. Okay, well, back to the work location choice. So this is the in other words, it's the this pi here governs how the job search location DW trans into a realized work location. Okay, or so how you go from one work location to another one depending on your choice. And then, of course, when you don't know, when you make a search decision, well, then you need to make an expectation about the outcome of that decision and calculate the expected value of that. And this is what we have here. So we integrate out the job search process, if you will. Okay, so that's going to be your x and the expected choice specific value function corresponding to a specific choice of intended work location, DW. And then once this is what is feeding in here to calculate the expected value before learning about the job search process and the location shocks, and then you can also calculate the probability distribution of the discrete choice of work location, or the choice probabilities. And again, these are given by logit formulas, and because of this one being ID extreme value. And this is the scale factor that we have on that ID extreme value term. Okay, and we can normalize one of them to 1 so we don't lose identification once we start estimating the model. Okay, so now having derived now the expected value here for the accept and expected values for work location, well, then we can derive the overall expected value. Remember, this guy here both it also contains the value of residential location. Okay, because we saw this in this sequential matter. But it's conditional on where you end up in the next period, right? So you need to also integrate out the non-location state variables to get the expected value function. And this is exactly like when we integrated out the Meyerich process here. I mean, it's a little bit simpler here because these are not depending on the choices. So we are assuming here the transition density for the state variables x is essentially not only conditionally independent, completely independent on the shocks and all the labor market probabilities Pn and Pk, pi n and pi k. Okay, so that's kind of, yeah, that ends the recursive formulation and description of the Bellman equations, and like I said, now that you have the expected value, well, then you can move back to move on back one period and solve again, which is corresponding to starting on this slide where EV is entering, and then you have your full mapping from the expected value to the expected value the period before, and then you do your whole 9 yards with backward induction throughout the life cycle. Or if it was a fixed point problem due to an infinite horizon model, you would try to solve for the fixed point and use successive approximations, or VFI, and the Newton-Kantorovich iteration, which is going to do backward induction. Okay, so that's a model. And we're now ready to talk about the structural estimation of that model. Okay, so we're going to take this model to the data and try to see if we can estimate all the model parameters. We can impose the various sets of functional forms and see if we can estimate the parameters of those underlying functional forms. But here's the estimation strategy. And because of all these kind of additional independence assumptions, we can estimate, like we did on the Harrow-Zucker model, we can estimate in several steps. So the first thing we will do is we're going to estimate parameters that governs the wage equations and transition probabilities for a children's state, and actually also Mary's state. I forgot to write that. So these are like exogenous. We take those things as exogenous. So I haven't even mentioned the wage equations, but those wage equations is essentially just going to be standard Mincer wage equations, wage equations that varies. Wages or income can vary across different regions, and it depends on the your education and so on. So this is basically the wage equation. It's in there. I think I'm going to skip talking about the wage equation. So we have spent so much time talking about wage equations and income processes in this study. Okay, in this education. So this is what you do in the first step. Okay, estimate everything you can without solving the model. Okay, and then we estimate reduced form demand equation, which is essentially this equation that we had right here that we derive from solving the static problem. So we're going to estimate this. Now notice here that this we're going to parameterize with a linear function. This is going to be a linear function multiplied by a variable that we observe and depends on an observable variable, the location that you choose to live in. And then it's divided by this parameter here. And essentially this ends up being a linear, if you ignore any potential corner solutions, and actually the model doesn't predict negative demand, then this is just a linear model, and you can estimate it with OLS. Okay, I'm going to show you the results in just a second. Okay, so this now everything here is we have estimated quite a lot of parameters already without even thinking about dynamic programming. And this is what we do in the third step: estimate the remaining structural parameters by maximum likelihood, applying the parameters that we have used up here. So we're going to stick those parameters in and hold them fixed. Okay, now you can have a fourth step where you estimate all these parameters jointly if you want to impose the cross-equational restrictions that these equations imply, and let also the wage equation's parameters be affected by the likelihood of the discrete choice of work location and account for that selection in that way. But we're going to do it in this simple three-step procedure. So what is the likelihood looks like? Okay, so the maximum likelihood estimator is obtained by maximizing with respect to the structural parameters. So this is the remaining structural parameters. The sample average, and maybe there should be a t here. That's kind of a little bit, no, that's not going to be a t. Okay, that's going to be this is the likelihood function for, or likelihood contribution for a particular individual, and then we take the average likelihood, or an average over the cross-sectional units. That's how we do it. Okay, so what is this comprised of? Well, it depends on the log of the probability of residential location, and then the log of a probability. Oh wow, there's a log of this sum. So this is the choice probability, right? and this over here we got the transition probabilities for that governs the process for the job search process. So this is how we integrate out the stochastic elements of the job search process in order to get something, the likelihood in terms of observables, because we don't observe people's intended work location, we observe the work location outcome. Okay, and for that, well, we need to wait with all the probabilities that those work location outcomes can happen. And this is like a mixture of choice probabilities weighted with those transition probabilities from the labor market. Okay, so but this is the likelihood. There's these two choices, and this is what we put into the likelihood. And you can have, if you try to match more likelihood, if you have wanted to have the write up a likelihood for the housing demand, well, then you would just add that log of the housing demand likelihood and then estimate those parameters too. Okay, but since we're already fixing those parameters, we're not going to include those in the likelihood. Okay, so and then we proceed in the spirit of the nested fixed point algorithm, except that, of course, we're going to do backward induction instead of solving fixed points, where you start searching for parameters here, and then for every evaluation of the likelihood function, well, you need to solve for those choice probabilities. That essentially depends on everything that we solve for on these slides here, and we do that by backward induction. Sorry for going so fast forth and back, but it's just to remind you that we spent some time solving the model. Okay, so that's the estimation strategy, and we're now ready to go to the results. Okay, so I'm going to present together the functional forms, parameter estimates, and the model fit. Because it's just nicer to have the equation you're estimating next to the results. Okay, so we're going to start with the housing demand. Okay, I'm not going to spend time on how to estimate the wage equation. The wage equation is already estimated, and we would be able to predict for any state and the model and for any decision what your wage is going to be. Okay, in case you end up and get a job in that work location. Okay. So that's, we're not going to spend time on that. So we have this this is the part of the utility function has to do with the housing demand. Okay, and I'm repeating myself a little bit here, but this is essentially just a utility, and then you assume that yes, the diminishing returns to house size, so this phi h2 is negative, and then we could derive the housing demand from the first order conditions, like we saw. It has this form here, and then the job now is to put functional forms on those coefficients that enter into the utility function. Okay, so we got the market utility of money, which we're going to take to be linear in income, and to allow for richer people just to put lower weight on money, just to as a reduced form of throwing out any choice of consumption, savings, investments, all this kind of wealth accumulation. Just it's like richer people in terms of income usually just also have wealth, and then they are less concerned about spending their money on housing. Okay, so this is just to allow for that. Okay. And then you have this phi here, it's a function of x, that enters on the linear term on the utility of housing, and thereby determines the level of housing. And we let that to be heterogeneous as a function of age, marital status, and children's status. So essentially, if you estimate this to be positive, then married people just need more space for a given amount of income. Okay, so they put more weight on having more space and are willing to substitute that for other goods. Okay, that's what this would mean if this was positive. Okay, and then housing cost. Well, that's we already talked about the user cost times the price of the house, and then essentially the square meter price here depends on where you choose to live. Okay. And this is absorbed. So all this together imply this linear regression, and we can estimate that. Now, there's one thing to note here is that all these coefficients here, even though they enter in linearly, this ends up with a linear regression, they're going to be divided by this phi h2, okay? And And this means that all the parameters we are estimating would be parameters that enters into these the structure parameters phi here that enter into the marginal utility of housing, and the kappa parameters that index marginal utility of money. They would be estimated up to a scale here. So what we're going to actually do is you just do the linear regression by including all these variables and these variables interacted with a price, and then we're going to try to see if we can estimate the parameters, these scaled parameters. Okay, and this is what we have done here. So you can see what it is that we are estimating. So in order to be able to identify those, you need to bring in more information. Those two things separately. Okay, so here's a constant that's kind of, you can think of this as measured in square meters. Okay. Everything here is measured in square meters, so people demand a lot of square meters, but then you demand more if you are married, and if you're even more if you have children, and then there's also an increasing demand for housing in age. Now, this is before we have subtracted the part that has to do with prices. So on average, this does not mean on average that people, they have 150 square meters, because they are expensive and they have to pay for their houses. Okay, and so here's the coefficient of the price per square meters, which is marginal utility of money times the user cost divided by this, scaled by this the curvature parameter here, and that's negative as expected. So it's this downward sloping demand curve, and this means since this is negative, we're going to try to see, when we estimate this is going to be negative, the curvature parameter, we expect this to be positive, right? So on all these coefficients, they actually seem to make sense. So you can say that if you, given this is negative, you're going to have positive marginal utility of money that is decreasing with income, okay? And then we move on to estimate the choice model. Having estimated this regression and holding fixed dose constant, you can basically, for a given value of your guess of phi 2 and this other unidentified parameter here, you can go and estimate, you know what the expected demand is because these coefficients here are fixed from that regression. And then you move on and estimate the choice model, and here are some of the results from the parameters we're estimating. So the coefficient on h squared is going to be negative as expected, and the user cost of housing here is 0.24. Now this sounds like a lot, okay, but actually this is because we are measuring housing expenditures after taxes, and we're measuring income before taxes, and we found out about that after estimating the model. We're going to change that, but if you do a back of the envelope or a calculation and count for taxes, it's much more closer to something like 10% or even lower, which is not totally out of the realm. Okay, so then you have the parameters that index the marginal utility of money is going to be 0.8, and then that's going to be decreasing with income. So richer people, they have a lower marginal utility of money, and it never goes negative. So here's a model fit, okay? And the model fit actually is only something that depends on these coefficients here for the model fit for the housing demand over the life cycle. We see that the housing demand is increasing over the life cycle, and then it's kind of flattening out. So at the middle of life, where people have children and are married, they demand a lot of housing, and then at some point, either kids move away, you get divorced, partners die, and then you downsize. Okay, and if you look at how it fits across the across these different values of the state variables, it also seems like we're doing a reasonable job. By the way, crosses here means the prediction from the model, and circles, that means the red circles here, that means the data. So if you have a cross inside a circle, it's like a perfect fit. It's like a bullseye, right? Okay, and here the colors mean something else, but the crosses and the circles, that's essentially the model and the data. Okay, and so if you divide by children, you see it really shifts up the demand, And if you divide the predictions here by marital status, you also see that married people, they demand more, just like the model implies. We're not able really to. This is by education. You got the highly educated here in the gray color. You got the medium education, and you got low educated here down here. So you got the pattern. The more highly educated people are demanding more housing. But we're not entirely capturing that highly educated people are not downsizing at the end of the life cycle. This is most likely because we don't have wealth accumulation and we don't have any adjustment cost. So this is this is what we see in the data. So we're making this mistake, this approximation here. Okay. One thing that is nice though is that this is, we're dividing by schooling, but if you look at the equation here, schooling doesn't enter at all. So where does schooling enter? It enters by shifting up, down, and down income, since schooling enter into the income equations. So this effect here is coming simply just because richer people are demanding more housing. Okay. Okay. Now, we also allow for regional amenities, and we have, as of now, in the current state of the model, we have not estimated all the regional amenities, or we've not included any observed amenities. We just, included a bunch of fixed effects to control for it. Okay, and you can estimate those fixed effects, and that's going to be just essentially a parameter for each region, and all these parameters, they are right here. I think Copenhagen is the outside option, so this is a flat expert, and then you can see it's just essentially less cool to live in the rest of the country. Okay, and of course these are things we want to broaden out to actually really try to see if we can model what those underlying amenities are. What is it that consumers are putting high utility on? If it's restaurants or quality of daycare, quality of schooling. What is it that it's because these are things that drives up the prices of different regions over and above what is coming from the labor market in terms of job opportunities is going to be indexed by the pies that we are also trying to estimate. Okay, so job arrival and dismissal. These are the pies that enters into the job search process. We're gonna parameterize them to depend on the age of the individual and whether you're unemployed, what the job density in the region is, and some educational dimensions. And the same thing with the keeping your job. Okay, so we put them into logit formulas essentially because we just want some functional form for these choice problems to make sure that they lie between 0 and 1. Okay, because these are probabilities, so you should make a restriction in your model. Make sure that you pin down those coefficients to add up to 1 across all the outcomes. Well, here's a binary one, so it's just 1 and between they should just be between 0 and 1 because all the other outcomes are 1 minus those probabilities. But so that's by construction. But it's a good way of, if you have multiple outcomes, you can also use logits. But here, for the binary outcomes, it's not really actually a big parametric restriction to put a logit around it. Okay, so here's the parameters from the job arrival and dismissal. So we had a constant. This is the probability. This is the probability of keeping. This is the probability of a new job arrival. Okay, so there's these parameters. You would have to actually calculate the partial effects in order to figure out, to really interpret them. I'm just going to interpret on the sign here and not the magnitude, okay? But generally the probability of keeping jobs is increasing in age, so the people are more stable, and then and there's less, that's essentially less turnover. And then the schooling, highly educated people, they are, I think the reference category here is the low educated people. So highly educated people, they have a higher probability of keeping their jobs. And if you look at the probability of a new job arrival, well, then the highly educated are those with the highest job arrival probabilities. So they're not. The job separation is a little bit lower than medium educated, but they have a higher probability of of getting new jobs. Okay, so there's a little bit more turnover for the highly educated, which kind of it's expected. Okay, and then the probability of getting new jobs is declining in age and so on. There's also a disutility of work parameter that we include into the model, which is positive, and that's kind of expected, right? So you like the money, but you don't necessarily like to work. Okay, so you can put it, anything into. In principle, you can parameterize so that it depends on all the state variables, and you can construct variables that depends on the state variable. So think about a state variable. That's a set of regions. So you can have lots of regional specific variables, like what is the job density of the education associated with the education that you have, for instance. Okay. Okay, so we also allow for utility cost of moving residents, which we also take to be a functional linear functional form. So you pay only the moving cost if you are moving a resident. So this is like indicator for that being the case. So otherwise, moving cost is going to be 0. There's a constant: age, marital status, children's status, and then a bunch of educational duties. And the results are as expected. That the psychological moving cost is increasing with age, increasing with your married and your children, but then the less educated or the more educated people, highly educated people actually have lower moving costs and more mobility. You can also estimate the commute cost, and we've done that. Okay, and the commute cost in our current specification is essentially just a constant that we estimate. It's positive. Okay, so that's kind of nice. People, this is a parameter that makes people live closer to make the model predict people live closer to their workplace or try to live closer to their workplace. So here's some. So that's essentially some of the models. So here's a model parameters. Here's some model fit, and here you got the observation. This is the area we're looking at, and this is the residential sorting that you see in the data. So in the Copenhagen area, in Copenhagen municipality and Frederiksberg municipality, people are just generally younger. Okay, you got the color here, dark. That's young people, and this model is able to predict that. Okay, so this is a simulation from the model. This is the observed. This is essentially just averages from the data. And then the same thing with the sorting of couples, although the model predicts less couples living up here. Okay, but otherwise it kind of gets the same patterns, although not perfect. It does give the same patterns as residential sorting. Okay, the same thing with children. If you look at the sorting of the highly educated people, the model also predict that it's a highly educated people who live. This is by home. This is by work location, the residential location choice and work location choice. It's the highly educated people that live north from Copenhagen, where in Gentofte here, where houses are also more expensive. And this is what you see in the data. And there's a lot of highly educated people, more highly educated people centered in Copenhagen. And this is also predicted by the model. Okay, if you look at where people search for jobs, it's also pretty much capturing the same distribution. Oh, it's not perfect, it's not exactly the same colors, but the pattern is reasonable. Okay, so you got essentially highly educated people centered north of Copenhagen and in the center of the city, with respect to jobs and also with respect to the residents. Okay. So this is a work location. I think we actually looked at that. So here's some life cycle profiles, and these are things that are coming out of the model, just are the choice model. Okay, and again, crosses here, the black one in this case is going to be a model prediction, and this is the red ones are the observations, and we will see it does a fairly good job of living probability. Predicting the share of living in Copenhagen. So this is going to be a graph like this for every municipality that are in the area of analysis. But we'll just focus on Copenhagen, and you see it's shifted up by marital status, and also it fits by schooling. So that's more highly educated, especially the young, highly educated people live in Copenhagen. By the way, I forgot to say age is on the axis on all these graphs here. Okay, and then by children. Here we got people without children. They're more likely to live in the city of Copenhagen, whereas they start to move out of the city when they get children. So this is probability is just lower. Okay, so it kind of fits what you see the stylus fact we saw in the data, that the people living in Copenhagen or in the urban areas more generally is the young people that are highly educated, have no children, and are singles. Okay, so here's the moving probabilities. These were essentially the levels, right? So here we got the moving. So these are the transitions of the work location state or residential work location state that we're modeling, and it's downward sloping. So, and here's another example why it's important to have a life cycle model, right? Because you clearly see this life cycle pattern not only here but also, in virtually all the graphs you're going to see here. So here's the this is like what we saw in the beginning. People less likely to move as they get older. There's in this data set not that so much variation as we saw in the Danish population. So we're zooming in on a small area. So maybe they're have that as much variation as you have in the entire country. But you still see some of the same effect that if you have children. Red one here is children. If you have children, well, then you are simply just less likely to move. It's just more costly to move, and the model also predicts that. Here, if you look at moving residents to and from Copenhagen, now it's going to be harder to start fitting the moving patterns in transitions in and out of certain regions, but we are still getting predicting some of the patterns. Yeah, it makes sense. We're now making moving costs specific to where you're moving, and maybe it's a place where you should consider revising the model. Let's talk about the work location choice. So here's a share of people working in Copenhagen. It's not as clear cut as a residential location choice, but still you got you got some of the overall patterns pretty okay. So the share of working in Copenhagen is declining. Both because people are moving jobs out of Copenhagen, and then also at some point here, near the retirement, then people just move to the work location region, which is not working, which is retirement. So this is both a choice on a labor supply choice and a choice of not working in that particular region. You got the same shift by schooling and age. It tracks it parts of the life cycle, but not perfect everywhere. Okay. Here's the transitions for the move of work locations, downward sloping, and again it becomes much harder to do moving work location to and from a particular region. So we have something to improve, but really, I think it's very instructive to look at these graphs, right? I mean, this is a place where you can see, here's a model not perfect fitting. Do you want to do something to try to fit that? Well, then that graph is going to guide you in how you can improve on your specification, okay? So this is what you should do when you make empirical work with structural model. Try to make it like lots of dashboards of graphs with model fit, so you can see how the model is fitting with all sorts of dimensions of the data, and look at it while you plot them, while you're trying to maximize the model. When you're trying to add more and more parameters, when you're improving on the specification, look at these graphs and learn about where the model is not fitting, and how one parameter that during the search over the parameter space, how that's moving up and down the prediction graph to make the fit better and better as you maximize the likelihood. So you can this is a key thing. It is to produce graphs that compares predictions and observation, and not just look at parameter values. Okay, because parameter values, well, that's just not enough information. Now here's another graph, And this is, I would say, this is this is the outcome of two choices. It's both the residential choice and the work location choice combined. So here we got the commute time, which is essentially the distance between the two. And you see here a very, very, a close fit overall, okay? And it's not like we have like put in a bunch of dummies, age dummies, to account for that commute should really have this particular functional forms, or splines or neural nets or machine learning or anything. This is a combination of several things. And look at the functional form is very different across the different compositions by the states. So it's a combination of both the demographics changing, right? I mean, as you get older here, you start to get married and children, and this means that you move from one curve to the next, right? So when you get married, you move up. When you from this curve to this curve, when you get children, well, you move from this curve to that curve, right? So this is a combination of different policy functions for different states, and then for the state transition combined, and so the overall pattern here makes is a result of that. Okay, so it's not like we put in a dummy here for being older than 40. This is because you simply in this area you just form the families, and yeah. Okay, so. Okay, so commute cost commute cost will be the main parameter here, right? But that's just a constant, right? Everything is the same for everyone. Okay, so this is an outcome of optimal choices of both residence and work location, taking into account that moving cost parameter. You can say a little bit, the moving cost parameter, since you're just moving up and down the levels. At least it's not affecting people very differently because of the additivity in the model, the additive utility function. Okay, so this is basically the estimation. So let's move on to talk about equilibrium. Okay, so I talked about equilibrium in the beginning. So we can essentially compute the equilibrium at the housing market by comparing demand and supply, right? That's what you do. And what is equilibrium? Well, that's the price of housing per square meter in different regions. Okay. So we can search for equilibrium prices and put supply equal to demand. And we've already, the whole choice model is a model that gives both supply, gives the demand and supply, if you will, for of housing, depending on how you look at it. If you look at it, transitions, you would have both sides of the market. If you move out, if someone is moving out of a house, well, someone else would have to buy it. Okay. Now we can look at it in levels and then just take the supply of houses in a given region, the stock of houses to be fixed, and then the demand is going to come from the model. Okay. I mean, you can formulate this in either way. It's going to be the same. Okay, but in order to set supply equal to demand, we'll need to search for the equilibrium prices to adjust the total expected demand, which we'll call D, in each residential location for houses measured in square meters. So we're going to write that in just a second. Okay, so the amount of houses demand. Remember, when you estimated demand function, we were conditioning on what people were living in a certain region. So we need to combine that with the choice model. Okay, that tells where people would like to move. Okay, because both things depends on the prices. Okay, so we got this demand, and then we just measured in square meters, and then that. Should equal the inelastic supply in each residential region. The housing supply, we just calculate from the data, which is micro-aggregated observed square meters for housing for people living in a particular region in the beginning of each period. So this is essentially
the data. And here we adjust for whether there's, since with two model demand at the individual level, we adjust for the number of people in the household, whether there's two adult people, so that it doesn't double count people that are married, because they will appear as two different individuals. Then there's the expected demand, D, which is a population average of housing demand weighted by choice probabilities of either staying or moving to a particular region. Okay, so this is where, I mean, you could do it in different ways. You can also look at how the demand is changing. You could have the people who are staying not being part of the model. Demand, but we're doing it in this particular way, and looking at the stock of the expected housing demand, including also people who just choose to stay in the same region. Okay, and so it looks like this. So we summarize all the individuals and take the housing demand implied by the demand function that we estimate in the first step, and that was a function of the state variables, but also of the prices that we are searching. So we estimated that demand equation here. Where do we have the parameters of that demand equation? So this is the one we've estimated from the data, and in here there's a coefficient of the price per the coefficient to the price per square meter. Okay, so the price per square meter, that is what we're solving for, right? So this is going to change demand, okay? And this is a vector, one for each region. Okay. So let's move on. Okay, so the expected demand looks like this. It's the number of square meter for people who live in a particular region, and then multiplied by the demand for living in that particular region. So this is the choice probability that individual in a particular state chooses to live in that particular region. And again, we weigh with the number of people in the household. So in other words, just to make it short, we take housing supply as exogenous. So we take a short run perspective. We're not looking at how the equilibrium housing supply is changing as the house prices changes. That can happen in the longer run, but then you would have to add a construction sector or a supply side in some way. Okay, we don't have that. We just keep supply fixed. And then we calculate demand, and both of them, and demand is a function of this price vector. Okay, and then the idea is that to compute the housing demand, house market equilibrium, we search for the prices that put supply equal to demand in all the different regions. Now, and of course, you make one region very expensive, then people's going to move out, and there's going to be, excess supply of houses, and then you don't have an equilibrium. You make it very, in a region very, cheap relative to the other ones, compared, given the level of attractiveness, everybody's going to rush into that region, and that's going to, create excess demand for houses and then drive up the prices. But in equilibrium, supply is equal to demand. Okay, so you search for this R-dimensional vector. There's a price for each region in order to equalize the left-hand side and the right-hand side. And we do that. Okay, and this is actually quite easy, because what do we have here? Well, we have a constant here, and then we have something here over here, which are essentially smooth functions of the prices. Where do the prices enter? In here, this is a linear function. And in here, well, this is the logit probabilities, and they're entering into the utility in a smooth way, and into the logit formula in a smooth way, although a complicated way, but in a smooth way. Okay, so you can just differentiate this and calculate derivatives. And then you just do your Newton's method, okay, for solving nonlinear equations. So using this very fast derivative-based equation solver, and we can even calculate those derivatives analytically to make it even faster. Okay, so it works very good, actually, and that's one of the nice things about the closed form solutions for choice probabilities. You get the smoothness, so you can use derivative-based methods such as Newton's methods. So here's the result of the a model fit for a particular for one period, where you have the prices in the data that what we have observed. This is what we use to estimate the demand equation from, and then you got the prices predicted from the model, and you can see we are doing a fairly okay job. They're all on the 45-degree line, and this means that we have like almost like a perfect sorting of the different different regions in terms of prices that are fully in line with what is predicted from the data. Then if you do this year by year by year, and then the idea was the model should predict the price graph with the dispersion you saw in the very beginning. Okay, now we've all just estimated this sort of pool samples is going to just be one price. Okay, and we're working on making that graph. Okay. So here's the summary of the model fit. The estimated model closely tracks the observed life cycle patterns and captures key aspects of worker mobility and residential sorting. House price is almost perfect linear. You utilize that when you specify the model. Regional price per square meters is decreasing in distance to high density areas. You got housing demand increasing in family size and income just as expected, but then they're decreasing with prices. We saw that from the housing demand equation. The model is able to capture this trade-off between house size it's having this trade-off between house size and location near job and amenities, so that households commute longer as they grow in size and they therefore demand more space. This is why you see all the people move. The model is able to predict how people are moving outside Copenhagen looking for more space, and that commute time is increasing throughout the life cycle. Without the housing choice, you wouldn't be able to predict house size choice, and that trade-off, you would not be able to predict that that transition over the life cycle. Residential sorting of highly educated into urban areas. This is a place where a monocentric city model would really be a poor approximation, right? You saw it's not only about the distance to the central business district, because it's the highly educated. They live north from Copenhagen, not south from Copenhagen. It's not that the rich just are sorting into being close to the economic activity. But they are into the center of the business district. Some are searching north, and rich people are north, and poor people. I mean, it's not like nobody's poor in Copenhagen. I mean, not that many poor people in Copenhagen. So relatively to the high and low educated people are in north and south respectively. That would not be able to capture by a monocentric city model. Residential mobility falls with age, moving distance, when children arrive, when people are married, and when employed, and the model actually predict that. Except for with the moving distance, we actually haven't really accounted for that yet. Worker mobility falls with age and increase with education, and you get to see this clear simultaneity in residential work location choices. That we've actually not really highlighted here in the model fit, but I can tell you that's definitely predicted by the model. We've looked at that data too. So equilibrium prices closely tracks the observed price ranking and overall price levels across the regions, as we just seen in this graph. So overall the model is doing pretty okay in terms of predicting the outcomes that we care about predicting. Now, so finally, we want to do, now we've estimated the model, do counterfactual equilibrium simulation. Okay, so we're considering two counterfactuals here. One is a 5% higher housing supply in the center of Copenhagen, and then another counterfactual would be higher commute cost. Okay, so the model here predicts that urbanization really increase if you increase the higher supply of housing exogenously, because there's more space for people. Okay, so more, but it's not only that if you make more space in the center of the city that that people just, the people who live there demand more space. It's also that more people are moving in because the more space drive down the prices and makes it more attractive to live in Copenhagen. Okay, so people move towards Copenhagen away from the rest of Zealand and surroundings in the Greater Copenhagen area. Prices fall in all regions, but most in Copenhagen. Of course, that's a result of increased supply. And then the sorting based on income also changed. So average income actually increase, for example, in Copenhagen. These are examples of counterfactuals you could do within this this framework. So these are, this is pretty preliminary examples, and of course you can do lots of different things. This is a cool thing of structural modeling. You can, with this model, have there's a whole distribution of transitions of jobs and commute choices and work locations and housing demand, and how that varies across the population. You can analyze that from the model. The model predicts that fully because it's a fully specified parametric model with all these choices. Okay, the second counterfactual, well, that's increasing commute cost, which kind of, a stylized way of saying what is happening if we just let congestions on freeways increase and do not invest in infrastructure or in public transport, and it just takes more time to get from A to B, or it becomes more costly to get from A to B. Well, if commute cost is increasing, well, then commute time it actually ends up dropping for all workers. Why? Because you don't want to, pay for, or you want to, if it becomes more costly to commute, well, then you're going to commute less, okay? If you commute less, well, then you need to live closer to your workplace, and if the jobs are in Copenhagen, that's where the prices are going to increase, because there's an increased demand for houses or for dwellings in Copenhagen, pressuring up the prices there, and then the equilibrium prices fall in the rural areas of Denmark, especially in the outside option, the rest of Zealand. So that's kind of very intuitive, right? It makes it very expensive to get into where the activity is. Then the prices is going to fall in the areas where there's no activity, okay? Because people don't like to commute to jobs. So another thing is, and that's like a supply effect, is if you increase commute cost, what's going to happen is that some of the people are going to be staying at home, so they're going to be retiring, or they're going to just be unemployed, voluntarily unemployed, because it's just not worth it to do that commute to get into the jobs in Copenhagen. That's a prediction from the model. Another intuitive one. So these are like arguments for actually, making public transport available, making transport very efficient. It is that it reduces the inequality in prices across space, and house prices levels them out, and it also increases labor supply. And then it also increases utility for workers because they don't have to spend so much time in the car or in the train, or spend money on it. So it's not like it's a no-brainer just to decrease the commute cost, but at least it illustrates some of the things that are associated with that and make this graph. So here's some of the results. I think I talked too long already. Basically, these graphs here, they just illustrate what I just said at the bullets. Okay, so increased housing supply makes the house prices decrease more in Copenhagen. The increase in commute cost, you can see here. This is a distribution of simulated change in commute time, and some of these peaks are actually corresponding to people who go from commuting along to not commuting at all because they're staying at home. Okay, so I'm going to skip all this and just conclude. So we estimate a life cycle model for that simultaneous tracks a large number of mechanisms, residential location, job source, work location outcomes, and resulting commuting, demand for square meters, equilibrium house prices, and simulated the effects on house prices and job mobility, residential sorting, and commuting, and computed two counterfactual equilibria for increased housing supply in the center of Copenhagen and increased cost of commuting. This is the first draft where current working on further refinements of the model and simulating more counterfactuals. So here's some plans for future research. We want to have more heterogeneity in the wage equation, so I haven't talked much about that. For instance, persistent income shocks. Okay, we want to have estimate a choice model that in a better way utilize the high quality panel data that we have in Denmark and able to predict how the price changes over time, which is about essentially repeating estimation of the model for all the different time periods, or repeated solving of the model of the different time period, which is why we haven't done it yet, because it just takes a longer time on the computer. We want to increase more regions around Copenhagen area, ideally entire Zealand, or eventually when we break the curse of dimensionality, the entire Denmark. Okay. Then we want to include more time-varying regional amenities and allow for taste variation across different types of individuals in that. We want to have potentially an additional educational choice and add endogenous retirement in the model. So right now we are treating unemployment, and retirement in the same way. Maybe that's okay. And allow for more flexible substitution patterns than those implied by the nested logit. And Mogens Foskau, the professor here at the department, is working on something very exciting called generalized entropy models that allows for much more flexible substitution patterns across regions. And here we don't have the IIA because we have so many different choices that are we have the nested choices and so many cross-equational restrictions, but still, those shocks to residential choices, they're uncorrelated across space. Okay, those shocks to work location choices, the epsilons, they're also uncorrelated across space. So once you start looking at entire Denmark, it's very unlikely that the shocks that are located near each other are more closely correlated than those that are far away from each other. So allowing for that is a bigger job. It's almost like if a whole life research agenda, but this is something I really want to learn from Mogens and how to see if I can figure out how to put that into dynamic programming models. And then we want to look at some more specific counterfactual investments, like what is the impact of the new metro? What is the impact of the a bridge from Zealand to Jutland over Kattegat? Specific infrastructure investments where you can use transportation models to predict how the commute time changes on specific paths on the network, and not just as a general change across all different regions, as we have done here. We can also extend the equilibrium to include the labor market and allow for congestion feedback in residential work location choices, really affecting the equilibrium and congestion. So that would drive up the cost of commuting. And here, in order to do that, you could just assume something like fixed capacity in the short run and see how other policies would affect congestion dynamics in this model. Look at a long run equilibrium with construction, so that the supply of houses is not fixed. And also have a labor demand side of the model. So there's so many different ways you can go to with this model, and actually this is actually good topics for your term papers. Okay, so take this model or a simplified version of this model and add one of those many things you can do, right? Or you can also add a state variable in a high housing demand choice, subject to adjustment cost, and try to get rid of that. Of that static assumption that we are making. So there's many things you can do that we haven't done, and this is subject to future research, or subject to very good ideas for you guys to write a term paper. So I'm going to stop here and wish you the best of luck for doing this. It's really fun. I really enjoy this.